Well, hello there. Today, we are going to talk about buffers and what happens when we add a strong acid or a strong base to that. So, we're going to see how this relates to like a titration curve, and we're going to be able to do calculations like that. So, I want you guys to understand conceptually first what will happen. And then, secondly, I want us to be able to look at the math and be able to calculate the pH once we've added that strong acid or strong base. So, let's focus on the conceptual component first. So I'm in our buffer notes underneath the calculations with addition of strong acid or strong base. So let's look at this first question here. We want to be able to calculate the pH when we've added 0.05 moles of HCl. So this guy right here is our invader, and it's a strong acid invader. And it's added to 1 liter of buffer solution in example problem 1. So we went through example problem 1 in our last video where we just had to calculate the pH of a buffer just sitting there. So it's just sitting there. It has its weak acid and conjugate base component, and we're not actually adding any strong acid or strong base to that. Okay, so we had acetic acid, which was our weak acid component, the HA, the acid component, and we had sodium acetate. Sodium acetate is a salt because it is a basic salt. It is a conjugate base. So one thing that I might not have relayed well enough in the last video or anything like that, I wanted to make a connection with salts, our salts video, and these conjugate bases that we have there. A salt and a conjugate base is one and the same. Okay, so when we have a basic salt, it's classified as a conjugate base. When we have an acidic salt, that is classified as a conjugate acid. So those are one and the same. So if you hear me say those things interchangeably, that's because they are one and the same. So we have our base component here and our acid component here. In order to figure out our pH, this is just a review of last video, it's always pKa plus log of A minus. Remember that the A minus is our base component. So it's always base goes on top. Okay. And HA is our acid component that is in the buffer. So it's base over acid. So what we did is we took the pKa value, so 4.74. We plug that in, log of 0.7, which is our base component, over 0.5, which is our acid component, and we got a pH of 4.89. The reason why I wanted to show you this is I want to show you how even if we add a strong acid or a strong base to this buffer, it doesn't change the pH drastically. It will change it just a little bit, but not much. So think about when we did our buffer lab and we made our titration curve, we had that buffer region, right? We kept on adding acid, or actually it was base, the NaOH. So we kept adding base, but our pH didn't really change that much until we reached that equivalence point where it spiked up. So we're looking at how exactly we could calculate the pH in that buffer range. So we'll be able to apply this to our titration curves and titration as a whole. All right, so conceptually, this is our buffer sitting here. We have the HA component, which is the acetic acid, and the A minus component, which is the sodium acetate. I just didn't write it out. So what we're doing here is we're adding strong acid. So if you remember, like, to the conceptual component of like how exactly buffers work, when this strong acid comes into this buffer solution, one of these components is going to react with the HCl in order to neutralize it. And that's the whole point of a buffer there. It neutralizes whatever invader. I call it the invader. Yes, I'm a sci-fi geek. Lizzie, I think you said that this was like a Star Wars kind of thing. Well, it is. It is, okay? I like Star Wars. Let me embrace this. So we have HCl coming in. That's our invader. So we have one of these components that is going to react with that. So since HCl is a strong acid, we're going to have the opposite component, so the base, react with that HCl. So if a strong acid's coming in, the base is going to react with that strong acid. Once the base reacts with the strong acid, if you remember from that, these are going to react and it's going to form more HA. So conceptually, what do you think will happen to the pH? Will the pH decrease a little bit or will it increase a little bit? Well, since I have A minus here, my HCl is going to react with that base to form the HA, the acid component, which in this case is acetic acid. Since I'm now making more acetic acid than I have the conjugate base, then what's going to happen there is my pH is going to drop a little bit. So this is like qualitatively what's going to happen. We know that my strong acid and my base component are going to react. I'm going to be forming more of the HAs. So therefore my pH is going to decrease a smidge. Now, that's qualitatively, that's conceptually. Now we have to actually be able to put the numbers to it and figure out the quantitative aspect, which is the numerical value. So we want to calculate that pH. Well, in order to first approach this, we have to understand conceptually what's going on, because we're going to have to be able to write a reaction and set up a Rice chart in order to figure out what's going to happen. This A minus is what we have present here. Well, what is happening conceptually, because this is reacting with the HCl, this A minus is going to decrease a little bit. Conceptually, this HA is being produced, right? So this HA is going to increase a little bit comparatively. Now they're going to decrease and increase by the same ratio. So what we can do is just set this up in a Rice chart to figure out what the new numbers will be. And if we know what these new numbers will be, we can figure out our pH by plugging it into that pH formula. So let me show you the step-by-step process of what we need to do. First step, we want to write our reaction of what's happening. Now, there's two ways you can do this, all right? If you're in a hurry and it doesn't ask you on a free response question to actually write out the reaction, all I have to do here is say A minus plus H plus. All right, so where am I getting that from? This is the base A minus plus the plus the H plus. We don't care about Cl, that's a spectator. We're worried about H plus is coming in or OH is coming in. So A minus plus H plus. And when those react, we're going to form the acid component, which is HA. You see how that's a really simple way to show you the reaction of what's happening. I also want to show you the real reaction of what's happening rather than just writing it like this, just in case you have to write it for a free response problem. So we need to figure out our base component. So that's the acetate. Sodium, remember, is going to be a spectator. So acetate is C2H3O2 minus. And that's going to react with the H plus. So acetate reacts with the H plus. And what that is going to form is the weak acid component, which is acetic acid. And guess what acetic acid is? H and this is going to come together. So it's HC2H3O2. So this would be the actual net ionic equation that is forming, that is happening when we have here. Okay, so again, if you get in a hurry, you can just do this. That's totally fine. Okay, in order to write this reaction, you need to understand conceptually when a strong acid's coming in, what does it react with? Well, strong acid reacts with base. So therefore, I'm going to form more HAs. So now that we have this reaction kind of written down, let's plug in our Rice chart. So RICE. Okay, so remember R stands for reaction, I stands for initial values. So let's figure out what our initial values are. We know our initial amount of acetic acid. Acetic acid is 0.5. So where do I plug this in at? It's at HA. So 0.5 is going to go here. We also know an initial concentration of the acetate. Remember what acetate is. We have to identify what this stuff is. That's half the battle. A minus. So I'm going to plug this 0.7 in for A minus. Now the next thing we have to plug in is the H plus. But here's our problem. We know H plus in forms of moles, and you see how this 0.5 and this 0.7 is in molarity. So what we have to do is figure out what the molarity of HCl would be. So we have moles, 0.05. We also know that there's 1 liter of solution. So what is molarity? It's moles over liters. So we would take this 0.05 moles divided by 1 liter, and that would give us our concentration, which, because it's 1 liter, that makes our math nice. It will be 0.05 molarity. Remember, everything in here is going to be molarity. So now, what's going to happen? All right, conceptually, what's happening? Well, all of this strong acid is going to be neutralized. So what that means is we're going to use up all of this strong acid here. None of that's going to be left over. That's the whole purpose of the buffer. We don't want any remaining H pluses, because if we have remaining H pluses, that's going to change my pH significantly. If I just change my ratio of A minus to HA, and I have to, I still have a buffer here, right? Because if I had H pluses floating around, then I wouldn't completely have a buffer. So I'm neutralizing this H plus. So now it's just changing my concentrations of A minus and HA. So that's not going to change my pH very drastically. And we'll see that with the math. So now, what's happening to A minus? Well, it's reacting with the strong acid, right? This is all a 1:1:1 ratio. Makes that very nice. So however much of the H plus I have in there is going to react, because it's a 1:1 ratio, with the A minus. So then I'm going to subtract 0.05 molar there. What's happening to the HA? Well, the HA is being made, right? I'm making more of the HA. So what's happening there is I'm going to increase that molarity by the amount of the acid that reacted. And again, the reason why this is the case is because they're all a 1:1:1 ratio. So what I basically did here is I used up all of the H plus. I subtracted it from the A minus because they're reacting with one another. So we said this is going to decrease. And we see that the math is showing us that it's decreasing there. The HA is going to be produced as a result. So that value should increase, right? So that's why we're adding the H plus amount here. And we showed conceptually that the HA should increase a little bit. So again, if you understand this stuff conceptually, that's going to make your math so much easier. So I hope I'm explaining it well enough. So we need to figure out our new values once this stuff has reacted. And those new values are going to be what we plug into here. All right, so I'm going to use a blue pen now to figure out. So 0.7 minus 0.05 is 0.65 molar, and that's of the A minus. And HA is 0.5 plus 0.05, so that is 0.55 molar. So that is the new concentration of my HA. Now all I have to do is plug this value in for HA, plug this value in for A minus. My pKa hasn't changed because I'm dealing with the same stuff, and that will give me my new pH. So let's plug that in. pH is equal to pKa, so 4.74, plus A minus, log of A minus. We said that that was 0.65. Did it decrease a little bit? Conceptually, we said it should, and yes, it's decreased from 0.7. Over HA is now 0.55. Conceptually, we said that that should increase a little bit, right? And hey, guess what? It did. Yay. So now I work through the math. So 0.65 divided by 0.55, log of that value plus 4.74. So we get a value of 4.81 for my new pH. Now, didn't we predict conceptually that our pH decreased a little bit? And guess what? It did. We were at 4.89 before I added anything in there. Now that I added strong acid, my pH decreased a little bit, which is conceptually what we said should happen. So this is how we figure out our pH if we're adding a strong acid to that buffer. So let me get set up for number 2. Okie dokie. So in this scenario, we're still working with a buffer solution from problem 1. So we still have acetic acid, which is our acid component. We still have sodium acetate, which is our base component. So I just have A- for our base, HA for our acid here. Instead of adding HCl in this one, we're adding sodium hydroxide. So sodium hydroxide is a strong base. So let's figure out conceptually what should happen. Well, since this is a strong base, there's my acid component, there's my base component. This strong base is going to react with the acid component. And because that strong base is reacting with the acid component, this acid is going to completely neutralize however much came in. It's going to start making more of my base component. Okay, so strong base is reacting with my acid. When those two react, I'm going to produce more A-. So conceptually, what should happen to the concentration of HA? Well, if we go back up here, our concentration of HA should decrease a little bit. What should happen to the concentration of our A-? Our A- concentration should increase a little bit. And therefore, conceptually, what should happen to my pH? Should it decrease a little bit or increase a little bit? Well, because I'm adding strong base here and I'm making more conjugate base as a result, then I should see my pH increase a small amount. Now, is it going to be a drastic amount? No. It's just going to be a small amount. Why? Because the point of a buffer is to neutralize this strong base invader that is coming in. Okay? So let's talk about the math now. So what we have to do is conceptually figure out what's reacting, what's happening there. Then we can write out that reaction. So again, I'm going to show you the shortened form if you're working through it fast and just kind of plugging in stuff. And I'm also going to show you how to write the real reaction in case they want, in case they want you to write it for a free response question. Okay. So here, for our reaction, we have NaOH plus HA. This Na is going to be a spectator. All that we're worried about is the OH minuses. Like all we worried about was the H pluses here. Okay, because the H pluses is what will drastically change the pH there. The OHs is what will drastically change the pH here. So that's what we're wanting to neutralize. We're wanting to neutralize either the H pluses or the OH minuses that are coming in. So I'm going to have HA. The acid component is reacting with the OH minus. So when that is the case, what I'm going to do is form two things actually. One thing is I'm going to form H and OH, so I'm going to form water, but that doesn't really play a role. Remember, water is never included in our equilibrium expressions or our Rice charts or anything like that because it's a liquid. So that's not really changing anything. What I'm focused on is once H and OH comes together, what I'm left with is A-. And isn't that the A-, the conjugate base portion that we said we should be producing there? Okay, so this is our generic form reaction that we have. Now let me also show you the real reaction of what's happening. So our acid component is acetic acid, which is HC2, H3O2. That's reacting with the OH minus. That hasn't changed. Now our product, we're actually getting two products here. Water is going to be formed. So H and OH coming together, it's going to form water. And then we're also going to form the base component, which is the sodium acetate. The sodium there is just a spectator. You see how we crossed out sodium here? Well, it's aqueous here and it's aqueous there. So we just went ahead and eliminated that as a spectator. So we will have C2H3O2 minus. And this is our net ionic equation that we're dealing with here. So you can write it either way when you're setting up a RICE chart. If they said on a different free response question to write the reaction that occurs, then yes, we definitely have to write this form, okay? This, I personally just do this because it saves me time and I don't have to worry about if it's something that I don't really know, like formic acid. I've worked with it a few times, so I kind of know it. But if you don't know it, then you could just write that form out and you don't have to fret with it. Trying to make your life easier. So now let's figure out our information that we're going to plug in. So our RICE chart, RICE. So initial concentration of HA, it's the same as it was before. HA was 0.5. So again, we're referring to that first example problem up there. OH minus we'll look at just a second. A minus initially was 0.7. So now what's going to happen? Well, all of this OH minus, we have to figure out its concentration, remember. They're giving us moles. We have to figure out its concentration. So 0.05 moles divided by 1 liter is 0.05 molar. Now, we're going to get rid of all of this sucker. That is what our objective as a buffer is to do. Now, when we do that, we have to kind of sacrifice some of these HAs to do that. So we're going to decrease by the same amount we reacted with. Why is that the case? It's because it's all a 1-to-1-to-1 ratio. We're going to increase this A minus amount by 0.05. And so our new values, let me write that in a different color. Our new values is going to be 0.5 minus 0.05, which is 0.45 molar. Our new value here is going to be 0.7 plus 0.05, so that's going to be now 0.75 molar for my concentration. Now I'm going to stick this into my pH formula. So pH is equal to, same pKa, dealing with the same stuff there, 4.74 plus log of my base is A minus, it's 0.75. My acid, sorry, Kamala's up here. Kamala Khan, what you doing, my girl? Sorry. Okay, 0.75 over HA, which is 0.45. And now I'm going to solve for my pH. So 0.75 divided by 0.45, take the log of that value, and then we end up getting plus 4.74. You're distracting me, Kamala. And that value ends up being 4.96. So conceptually, did what was supposed to happen? Well, conceptually, we said that A minus should increase, and it did. Right? We also said that the HA should decrease, which it did, and therefore we decided that pH should increase a little bit, and it did. So that works out. Y'all want to see Kamala? This is my big girl. I love her. All right. So anyway, that is how you figure out the pH if you're adding a strong base. So let me get set up for the third one. Okie dokie, guys. So, getting set up for part 3. So, calculate the pH of a 0.5 liter buffer solution composed of 0.5 molar formic acid and 0.7 molar sodium formate before and after adding 10 milliliters of 0.1 molar HCl. So, here is what's happening. First of all, we need to be able to tell that which components of my buffer that I actually have. So we have formic acid, and you guys might not be familiar with what formic acid is. We haven't ever really used it. So formic acid is H2CO2. Again, if you get caught up with, not knowing what formic acid is, then we know it's an acid, so it's just HA. Okay. Then we have 0.7 molar sodium formate. Sodium formate is a salt, and we see because it came from NaOH and it came from formic acid. NaOH is a strong base. Formic acid is actually a weak acid. So that this is actually a basic salt. So we have a weak acid and a basic salt, which is aka a conjugate base. So that tells us that we have a buffer here. So this is my acid component, which is HA, and sodium formate, which we're not really worried about the sodium, we're just worried about the formate. That sodium is always going to be a spectator there. So the formate is HCO2 minus. That is the base component of the buffer, and it is my A minus. All right, so that's what we're worried about to be able to plug into here. So we want to figure out the pH before and after adding HCl. HCl here is our invader. So what is happening at the beginning? Well, pH equals pKa plus log A minus over HA. So what I would do is she's trying to learn with us. Hello, Kamala. All right, so what I'm going to do is plug in the A minus part. So A minus is 0.7. So 0.7 will go here. 0.5 is here. So 0.5 for the formic acid. Log plus pKa. pKa is the negative log of Ka value, which is like 3. Let me look it up. I did it over here. 3.74. Come on, get down. Sorry. All right. You got to stay down, baby. I got to do work. All right. So 3.74. Yes. So when I take 0.7 divided by 0.5, log of that plus 3.74, I get a pH of 3.89. So now, what should happen if we add 10 milliliters of 0.1 molar HCl? Conceptually, what's going to happen? We have HCl, and that is a strong acid. So which part is that going to react with? This is my acid component, and this is my base component. So strong acid reacts with base. When strong acid reacts with base, what happens as a result? You make more of the acid. So what should happen? We should see that our A minus decreases a small amount, our HA increases a small amount, and as a result, our pH should decrease a small amount because we're now making more HA than A minus, or we're making more HA basically. Right? We're making more of the acid component, so our pH is going to go down a little bit comparatively. So let's write our reaction. So remember, our generic form of the reaction is, let's see, we have strong acid reacting with the base. So A minus plus H plus, that's our strong acid component, yields HA. If we wanted to write this in a real reaction form, if it asked it in a free response question, then we would say HCO2 minus plus H plus. When those react, it's going to form the acid component, which is H2CO2. So that would be our real reaction there. So now let's figure out what our initial values were. So we have 0.5 for the formic acid, that goes here. We have 0.7 for the base component, so that goes here. And we need to figure out what our initial concentration of H plus was before we had them react. Now, here is where we have a different scenario from 1 and 2. Remember 1 and 2, we were given moles of the HCl. Here, we're given a volume and a molarity. So we have like a small volume, a small molarity of HCl. Well, when I put it in that buffer solution, it's going to change its concentration. Remember, whenever we change volumes, we change molarities, all right? So this HCl, in order to figure out its new concentration, because its volume is changing drastically, it's going from 10 milliliters to 0.5 liters. That's a drastic change in your volume. Because of that, we need to figure out what this new molarity is. We cannot, I repeat, we cannot just plug in 0.1 right there. Okay, so in order to figure out a new molarity when we change volumes, what equation do we use? We use M1V1 equals M2V2. This is known as your dilution equation. We're basically diluting this because we're adding a lot more volume to it. M1 is my initial molarity before I've mixed them. Okay, so this is kind of like a before mixing and an after mixing kind of equation, if you want to look at it that way. So M1 is going to be 0.1. V1 is going to be 10 milliliters. We need to put that in liters. So 10 milliliters will be 0.01 liters. M2 is what we're solving for, and V2 would be both of these volumes combined once they're mixed. So before mixing, after mixing. After mixing, these two volumes are going to combine. So it's going to be 0.5 liters plus 0.01 liters. So that's going to be a total of 0.501 liters. So now we're going to figure out our new calculation, our new molarity for the HCl. So I would take 0.1 times 0.01 divided by 0.501. And when you do that, you get a very small number, 0.00196 molar HCl. So I have to do this first before I can plug it into here. I have to figure out that new concentration. And the reason why is because I'm mixing two volumes and that concentration is going to change. Are you not comfortable? Hold on. All right, there you go. So we have 0.00196 here. Now, it's just like we've done before. We subtract that value here, 0.00196, minus 0.00196, and plus 0.00196. I know you can't read those, but all of these say 0.00196. I'm subtracting all of that H plus. I'm adding it over here. So now I have my new concentrations. Let me write that in blue. These are 0, 0.7 minus 0.00196 is 0.698. 0.5 plus 0.00196 is 0.502. Now I know what you're thinking. You're like, okay, well that didn't change it much. Well, that's the whole point of a buffer. You don't want these concentrations to change very much. We have a very low concentration and a very low volume, so that's why we do not see a drastic change here. Do not go into your whole rounding kind of thing. Some of you guys, especially in double period, like to round drastically. You want to have a give it out a couple of significant figures in order to figure out those actual quantities. So now we get to plug in HA's concentration, A minus's concentration, and find our new pH. Now remember, we predicted it to decrease a little bit. So let's see if that happens. So pKa is, it was 3.74, right? Yep, 3.74. And plus log. Our new concentration of A minus is, look here, 0.698. Our new concentration of HA is 0.502. And when we look and or do the calculation, I don't know why I said look. When we do our calculation, the pH we should get is 3.88. So did our buffer do the job? Yeah. We didn't change our pH very much, right? It was 3.89. Now it's 3.88. Conceptually, did what we predict happen? Did our A minus decrease? Yes, it did. Did our HA increase? Yes, it did. Did our pH decrease a small amount? Yeah, in fact, it did. So this is how you solve the problem if they do not give you moles of an invader. Instead, they give you a volume and a concentration of your invader. All right, so I'm going to stop the video here. I know it's been a lengthy video. I know that we have additional questions to talk about as well. Those additional questions are pretty simple. And actually, I think I'm just going to talk you guys through them in class, or I might make another video. It'll be a short video for that. So I'm going to stop this video here so you can focus on just buffers, how you find the pH if you're adding a strong acid and a strong base. I hope this is helpful. I'm sorry Kamala was just distracting me the whole time, and I'll leave you be. So have a good day. Toodles.